So when's the worksheet due? Tomorrow. Okay, good. And today is Monday, April 9th, National Winston Churchill Day. Did y'all read all of this?
Not yet.
What were y'all waiting for? Good, good. Everything we did in 6.1 we're going to be doing again in 6.2, but as I already promised, Ms. Schmucker, it's going to be easier. Okay? Because in 6.1 we were using the same techniques we're using here, but we had a vague target, like simplified to a single power of a single trig function. We didn't know what power, we didn't know what trig function. In this section, we're going to be doing trig proofs, which is an equation. So if we start on one side, the other side will become our target. So we have a definitive target. You just have to go into this section with a sense of adventure. Okay? You have to have your identities memorized, and as we go through each example, all we're going to be doing is extracting some strategies that might work in certain circumstances. So there's not going to be a single recipe that in a particular problem will get you from start to finish. Strategies are all you're going to have in conjunction with memorizing your trig identities. So one of my favorite quotes is by W.S. Anglin. Mathematics is not a careful march down a well-cleared highway, but rather a journey into a strange wilderness where the explorers will often get lost. And you will get lost, but that's part of the adventure, that's part of the fun. You can learn things from getting lost in these trig proofs. In other words, you learn from your mistakes, you back out, you don't make the mistake again, and you travel down a different road. In the spirit of National Winston Churchill Day, Churchill said never surrender, right? Never surrender. Never surrender. So that goes nicely with these trig proofs. Never surrender. If you get to a place where you get stuck, don't give up. Just see why you failed, back up, and try a different route. Winston Churchill had very, very, very many quotes, but some of the best quotes were his barbs that he exchanged with Lady Astor. A couple of which were, one time they were at a social event, and Lady Astor said, Churchill, if you were my husband, I would poison you. And he said, Lady Astor, if I were your husband, I would drink it. Yeah, good stuff. That's a good way to give a good comeback. Yeah. And Mr. Hyland apparently told one of his classes the other nice quote where he was drunk. Churchill was drunk at one of the events, like usual. And Lady Astor said, Churchill, you are drunk. He goes, that I very well may be, Lady Astor, but you are ugly. And tomorrow I'll be sober. Oh, face, right? Literally talking about her face being ugly. She'll wake up and still be ugly. So anyway, Churchill was very, very irascible. He was a curmudgeon, but very intelligent. And of course, there's that movie out where what's his face wins the Oscar for portraying him. What's his name? Gary Oldman. Yeah. Our Finest Hour. It's a good movie. So anyway, Gary Oldman, also Commissioner Gordon from the Batman. Yeah, also. Yeah, a lot of other things. Okay, so ready? Here's a toe-dipping example. A toe-dipping example, right? When you're testing the waters, you usually dip your toe in there, and you're like, ooh, that's deep, right? It's deep enough to jump in. Is that why is that what you test the waters with your toe? No. You usually dip your toe to measure the temperature. Unless you have really, really long toes, then you can measure the depth, right? Yeah. Oh, yeah, that's deep enough to jump in. Okay, here we go. So the instructions are going to be to prove the following identity. So the good news is this is not a strange journey into a wilderness. This is a well-cleared highway, but it's overgrown like on The Walking Dead. Okay? So think of it that way. This is a proof that is going to work. You know it's an identity in advance. That's not typically how things work. You're trying to decide if it's an identity, but you're going to know going in that it is an identity, so the left side does equal the right side. And you're not going to have to memorize this. Rather, you're just going to prove it using the fundamental identities and some algebra combinations of that you've memorized, okay? And some strategies that we're going to extract from these things. Remember the rules of proof. Draw a line down the equal sign. Whoops. Maybe a straight line that's vertical would be better. And your goal is to work on each side independently. Okay, you're not allowed to do what you can do like in solving a conditional equation. You can't add something to both sides. You work with each side independently until the left side looks like the right side, and when it does, you're done. You want to use fundamental identities. You don't want to put everything in terms of X, Y, and R. We don't do that anymore. If you get stuck on one side, you could jump to the other side, and as long as the bottom lines on both sides are the same. And remember, in the spirit of doing proofs and not Rachel's challenge, we want to tear things down rather than build them up. So which side to you looks like it has more information? The left side, actually. Yeah, very good, for a couple of reasons. First of all, both sides have two terms, so that's kind of the same. But the second side has two trig terms, whereas the right side has only one trig term. And if you also notice, the left side has a denser nucleus in that the powers are higher powers, right? Which could also be a strategy. Call on a higher power if you need to do so. And so there's more information there. So you start on the side that has more information that looks more complicated. You tear it down and look like the right side. Okay, so now if we decide to start on the left side, which there is no wrong side on which to start, you just pick a side, your right side becomes your target. Okay, so if you notice, the right side then is exclusively in terms of cosine. So my goal is to now get rid of the sines and pick up some cosines. But first I have to deal with the powers. I can't use Pythagorean identities unless they're squared. I don't have any identities memorized for them being to the fourth power. So there's some options you have here. You can call sine to the fourth of x 1 over cosecant to the fourth of x, but that's not going to get you closer to your target. So what could you do? I need to get down from fourth powers to second powers. Yeah, well, when you take the square root of something, it changes its value, right? The square root of 9 is not the same as 9. So if you did that, you have to take the square root of both sides. And that's not allowed in a proof. You can't do something to both sides. So that's not going to be something we could do. But we could do something that accomplishes the same thing. We could somehow factor it into smaller powers, right? Unmultiply it, if you will. So one of the strategies is to recognize something that's in factorable form. That is a difference of two what? Perfect squares. It's a difference of squares. As long as the exponents are even numbers, they're perfect squares, okay? And if you remember, a difference of two squares factors into the product of two whatchages? Conjugates. So the square root of sine to the fourth is sine squared, and same thing with cosine to the fourth. It's cosine squared. So you can go ahead and write your two square roots, and then remember one of them's plus and one of them's minus. So that's your first step, is to recognize that you need to make the power smaller by factoring. So recognizing special products is your strategy. Last week we looked at factoring trinomials in terms of sine squared and sine in order to get it down to smaller powers so we could solve it. So they don't have to be differences of squares. They can be factorable trinomials. All right, now that you do that, you kind of reassess, and something's slapping you in the face, right? 1. Sine squared plus cosine squared is Papa Pid. Okay? So we're going to replace that with 1. Now remember, you don't have to write the reasons, but if there is a reason, you want to write it. And the reason here would be Pythagorean identity. And now 1 times anything is itself. That would be the identity element of multiplication. So when in doubt, do not leave a step out. Remember, the process is the product, going from one line to the next. Very good. Now you have squareds, which is what you want, and now you can focus on getting rid of the sine squared. I would highly recommend anytime you make a Pythagorean or any kind of substitution, for that matter, you put parentheses around it. Pythagoreans especially, because they usually are replacing something with two terms. So now, how can I get rid of a sine squared and write it in terms of cosine squared? 1 minus cosine squared. So there you go. If you don't have your identities memorized, or even memorized to the point beyond just regurgitation, but knowing that they exist, you're not even going to know to go from that step to this step. So remember, you can manipulate them. And now, the parentheses show the substitution, but there's nothing to distribute, so you could drop them, and you can combine your cosine squareds. 1 minus cosine squared minus cosine squared is 1 minus 2 cosine squared. And if you compare to the other side, but for the font difference and the color change, is it exactly the same? It is. And so you're done. And so you can sign off now with your quote, which I would say here is, never surrender, in honor of Winston Churchill Day. Never surrender. Now, you could have started on the right-hand side, and if you wanted to see what that would look like, just work from the bottom up. And notice the hard step would be multiplying by a clever form of 1, knowing that the form of 1 you'd want to use would be sine squared plus cosine squared. That's the insight that would be involved with building something instead of tearing something down that's already there. All right. Any comments or questions on that one? That was a toe dipping example. So that was a relatively easy one. All right, so here is the wisdom that we're going to extract. Look to factor. Look for common factors. That's the first rule of factoring. Like we just saw, look for difference of squares, look for perfect square trinomials, and just things that factor as a trinomial. We saw both of those last week when we were solving equations. And at the end of this section, we'll review the formulas for the sum and difference of two cubes, because you probably don't have them memorized. But that's another thing to look for eventually. All right, so that's the strategy. That's the strategy that we are extracting from example 1. All right, example 2, it says to prove the following identity. That's going to get to be repetitive. Draw a line down the middle. That's the easy part. You got to start on one side. Doesn't matter which side. Remember, if you get stuck on one side, you can jump to the other. Ideally, though, for the extra challenge, try to stay on one side. All right, which side to you looks more complicated or has more information? You can make an argument right now that neither one of them looks more complicated. They both have two trig functions in them. The right side has one term with two factors. The left side has two terms, each with one factor. It turns out that the left side is going to be the easier one to start on because it has two terms, whereas the right side has one term. And this kind of then is another strategy. If you start on the left, then your right side becomes your target. So how would you get two terms into a single term? Well, to combine two terms, you need a common denominator. They already both have a common denominator of 1, but I can't combine them because they're unlike terms. So that's not going to really help. So the thing that could jumpstart this problem is to write either one of them or both of them in terms of something that has a fraction so that you could then get a common denominator. Right, there are a couple of options. You can either write both of them in terms of sine and cosine, which I mentioned last week is a really good strategy. Or in this case, you could just write tangent as 1 over cotangent because we already have a cotangent as the second term. Or you can write cotangent as 1 over tangent and leave them in terms of tangent, cotangent. Notice there are no tangents or cotangents on the right-hand side. You see that? So maybe if I did write it in terms of tangent, cotangent, that wouldn't be the way to go. So sine and cosine, I'll go ahead and do that since that's what Santi said. And maybe we'll come back and do it another way. So here you go. Let's put everything in terms of sine and cosine. Sine over cosine plus cosine over sine. That's using the identities. Now I have non-trivial denominators, so now I can get a common denominator. So there's two ways that you can combine these. The common denominator is the product, cosine times sine. So if you want to do the crisscross applesauce, butterfly multiply, that's fine, as long as you start in the top left. Sine times sine is sine squared. Take the middle sign, which is plus, and then the top right times the bottom left is cosine squared. If that were a minus, you have to start in the top left. Otherwise, that crisscross applesauce doesn't work. The other way is to multiply the first one by sine over sine and the second one by cosine over cosine. And that just takes a whole other line of writing. So if you could do that crisscross applesauce method, that kind of is a time saver. Saves one line. All right, and then you reassess. You got a single term, which is good. I spy Papa Pig now in the numerator, right? So that gets rid of a whole lot of baggage. That leaves us 1 over cosine times sine. And now you compare it to the right-hand side, and you're like, all right, what next? I got a single term, which is what I want. I got two factors, but they're both in the denominator. I need them in the numerator. Yeah, let's split this up. That's the same as 1 over cosine times 1 over sine. And now 1 over cosine is secant, and 1 over sine is cosecant. And if you compare that to the right side, secant times cosecant, does it look exactly the same? Yeah. Just kind of a note here, if you had flipped the terms or you had them backwards, if you had cosecant times secant, would you stop on that line? Is that exactly the same as the right side? No, you would need to go one more line and write them in the right order because that's the commutative property of multiplication. So make sure you don't stop until they're exactly the same. Again, but for a color or font difference. So now that you're done, you could sign off. And I'll go ahead and with another Churchill quote, I'll drink it, referring to the poison. There you go. Now, let's say you got to this line right here, 1 over cosine times sine. You're like, I am stuck. You probably wouldn't have that there. You could jump to the other side and be like, hey, if I have the left side in terms of sine and cosine, and the right side is not in terms of sine or cosine, let's go ahead and put the right side in terms of sine and cosine. That's 1 over cosine times 1 over sine. And now I have two factors. I'll multiply straight across. 1 times 1 is 1. Cosine times sine is cosine sine. And now if you compare it with the left side, are those the same? Yes. And you're done. It's another way to do the proof. It's better the first way when everything's on the left side, but it's okay to do it this way. In fact, if you did this, you can actually bring those steps now to the other side, because that's how it would do it if you were to keep going. Because what you've done now is you've created this circular loop of logic that you could jump in on any line and go clockwise or counterclockwise, and everything is equivalent to the line above or below it. Okay? So keep that in mind as another strategy. If you get stuck on one side, jump to the other. And as Diamond Rio so eloquently said in song, there ain't no road too long when we meet in the middle. Right? Yeah. You start walking your way, and I'll start walking mine. We'll meet in the middle neath the old Georgia pine. We gained a lot of ground because we each gave a little. Ain't no road too long when we's meeting in the middle. Okay, there you go. Comments or questions on this? The wisdom to extract. When all else fails, get everything in terms of sine and cosine. Well, nothing was really failing. That just kind of became a strategy. But if you ever find yourself stuck and it's not in terms of sine and cosine, you could do that. And then combine like terms by getting a common denominator. Those are the two things, I guess, that we can extract from that problem. Now, would anyone like to see it done another way? Yes is the correct answer. Yeah, good. Because as you see things done more ways than one, you're informing yourself of other options, all right? So here's another option. Tangent, cotangent. Let's just write that as 1 over cotangent. Why the heck not? And that's cotangent over 1. All right, so now we can get a common denominator. Let's do our cross product. 1 times 1, that's going to be 1, plus the other product is cotangent squared, and that's all over cotangent. Well, now in the numerator, what is 1 plus cotangent squared? That's a PID. That's cosecant squared over cotangent. All right, now if you look at the right-hand side, you're like, hey, I needed a factor of cosecant in my final answer. I have 2 factors of cosecant right now in my final answer. So I've got 1 of what I need. So let's go ahead and do this. Let's write cosecant squared as cosecant times cosecant all over cotangent. And now I'm like, I ain't messing with that cosecant, because that cosecant is already where he needs to be. So now all I really have left to prove, and I forgot my x here. If you ever forget your x, come back and put it, because I'll take off if it's not there. All I need to show now is that cosecant over cotangent is equal to secant. That's all I need to show. Well, I guess since this is a proof, that's equal to secant. So if I just went straight to that line right there, how do you think I would grade that? Do you think you showed me enough steps to show that? No. You would lose points there. I'm not convinced that you know why cosecant over cotangent is secant. It is, but you didn't show me why. So you would lose points there. So I'm going to be grading your quizzes, your tests, because there's so many different paths to the right answer. I'm going to be looking at every single line. So remember, when in doubt, to show it or leave it out, do not leave it out. So we need to go a little bit further by showing cosecant over cotangent. How can we do that? Well, if you're not sure how a quotient simplifies, put it in terms of sine and cosine. So now all else is failing, I guess. So that's 1 over sine times cotangent is cosine over sine, and that's times cosecant. And then I can say change flip. That's 1 over sine times sine over cosine times cosecant of x. And now your sines divide out. And now 1 over cosine is, in fact, secant. And I'm left with secant times cosecant, which is exactly what we have on the other side. So that also works. It's a tad bit more scenic. It's like going from New Braunfels to San Antonio by still going south, but maybe going through Seguin, Highway 78, McQueenie, Marion, Church, Cibolo, all those good. Yeah, it's a little more scenic. Takes a little longer. But you got it. You persist. All right? You persist. Churchill also said, when you're going through hell, keep on going. He also said that. All right? Any comments or questions on that one? Does anybody see another way to do it, or a different fun way to do it? They're all fun. Okay, let's look at example 3. Draw a line down the middle. I don't use that snap to line feature enough. There we go. Sweet. All right, so based upon what we just did in the previous one, what side makes more sense to start on, left or right? Left. Yeah. I've got 2 terms on the left, 1 term on the right. So I want to get 2 terms into 1 term by getting a common denominator. I don't have a common denominator. They look really close, but they have different signs. In fact, those are 2 whatchagets. Conjugates. That's kind of interesting. So if you want to do your crisscross applesauce, that works great. If you don't understand why that works, here's the correct way to do it. Let's get a common denominator. Their product is the common denominator. So on the first one, I already have a secant x minus 1. I need to multiply by a clever form of 1, which is secant x plus 1, the other factor. Times what's there, 1 over secant x minus 1. And then plus, this one has the plus 1, so he needs the minus 1. Secant x minus 1 over secant x minus 1 times what's already there, 1 over secant x plus 1. So this would be the other way to get a common denominator. Takes a whole other line of writing. But you're essentially multiplying by 2 clever forms of 1 to make sure that your denominators are the same. And so now you go to your denominator. Now what is secant squared of plus 1 times secant x minus 1? Sorry, secant plus 1, secant minus 1. That's a difference of squares, so you get secant squared minus 1. Your inside and outside cancel. All right, now on the top, when you multiply by 1, you get secant x plus 1 plus, and then times 1, you get secant x minus 1. So that's where we are right now. You could have gone from the first step to this third line, which is fine if you did your crisscross applesauce. But notice I went ahead and multiplied the 2 denominators together. Why? Because when you multiply the 2 conjugates, you get a difference of squares. And that difference of squares, secant squared minus 1, sure looks like it could be equal to something from the Pythagorean identity list, huh? What is secant squared x minus 1? Tangent squared, yeah. If you forget, go off to the side and write it out. 1 plus tangent squared is equal to secant squared. So secant squared minus 1 is tangent squared. So that's a huge strategy to try and remember. When you multiply 2 conjugates together, you set up a difference of squares, which sets up a Pythagorean substitution. Again, the product of 2 conjugates gives you a difference of squares, which sets up a Pythagorean substitution. All right, now is anything good happening in the numerator, like out in the hallway? They're jealous. We're inside. They're jealous. Yeah, what happens in the numerator? The 1's cancel, and I'm left with secant plus secant, which is 2 secant. Hey, look at the right side. Keep an eye on your target. I needed a 2. I got a 2. So I'm not going to mess with the 2 now. I'm not going to call it 4 halves or 6 divided by 3. I'm going to leave it as a 2. I got part of the proof already forming right in front of my eyes. That's great. I'm heading in the right direction. What's that? Yes, now I'm going to take notice here. I have a factor of cotangent in the top that I want. I have 2 factors of tangent in the bottom. By the reciprocal identity, 1 over tangent is equal to cotangent. So what I'm going to do next, and I better add my x there, I'm going to go ahead and split that up. I'm going to call that tangent times tangent. And now I'm going to leave this 2 and this tangent of x alone. In fact, on the next line, 2 divided by tangent is the same as 2 times cotangent by the reciprocal identity. You can just go straight from that to that, because that's like a times 1 over tangent. And so really now all I have to show is that secant over tangent is equal to cosecant. I need to show that secant over tangent is equal to cosecant. Well, again, if you just went straight to cosecant of x there, you're going to lose points. You haven't shown me how or why it's equal to cosecant. So what we're going to do is, since there's no cosecant already in there, we'll do what we did on the previous problem when we did it the second way. Do what? Right. If you ever have a ratio of 2 trig functions and you don't know how it simplifies, put it all in terms of sine and cosine. So secant is 1 over sine, right? And tangent is sine over cosine, right? No. If you don't have your identities memorized, it's going to derail for you, and it's going to get very, very frustrating because now you've deviated from the true path, okay? Secant is not 1 over sine, it's 1 over cosine. Yeah. All right, so now you have a complex fraction. You should rejoice when you have a complex fraction because the next step should be easy, and it's always the same. Get rid of the complex fraction. Now, you can multiply by cosine over cosine. That would be lick'em over lick'em. But because the denominator is a single fraction, you can also do state change flip. State change flip just requires another line of writing. So 1 over cosine, instead of divided by sine over cosine, it's now cosine over sine. If you wanted to, you could come up here and multiply by cosine over cosine on that same line, and then you can get to, it saves a line of writing if you do lick'em over lick'em. Okay, but whatever you'd be prone to do, just do it that way. And now, your cosines divide out. And what are we left with? We're left with 1 over sine, which is what? Cosecant. So I got 2 times cotangent times cosecant. And that I think is the right side. All you got to do is make sure the terms or the factors are written in the correct order. And they are. If they were flip-flop, I'd have to go one more line and commute them. So we got it done, so we'll go ahead and sign off, and I'll sign off with, this is hell. But I'm going to keep it going. But I'm going to keep it going. Keep it going. This is hell, but I'm going to keep it going. All right, whatever. All right. In fact, I'm going to come back up here and put quotations around hell. But since I've already used quotations, you know then to use single quotes. Right? Yeah. One man's hell is another person's heaven. I kind of like this. But I'm going to keep going because I want more hell. I think he meant eventually he'll get out. I don't know. I'm going to keep going because I want more. It's like another trip to the buffet, right? Oof. Got to get your money's worth, right? Stay for 2 meals. It's kind of camp. All right. Any comments or questions about this one? Extracting, again, you could do the same thing. Get 2 terms into 1 term by getting a common denominator. That was the same as the previous. So eliminate complex fractions. That's another one. And again, we also saw putting everything in terms of sine and cosine. Okay. You want to do one more? Let's do one more. Let's do one more. Prove the following identity. I'm going to give you a couple minutes to chew on this one on your own. Chew on it. Okay? By a couple minutes, I'll say 1 minute. Okay? At least you'll have maybe a good start on it. Because these really you should toil with on your own. All right, that's a minute. What side did you start on? Which side looks more complicated? Left? Why? Oh, it has a negative. I like it. There you go. That's about the only difference, right? The left side has a negative. I don't like negatives. They look pretty similar to each other. In fact, they almost look like reciprocals of each other, but they're not because one is negative. If you get stuck, you don't know what side to start on, they're already in terms of sine and cosine, so rats, it takes that away. They almost look like they shouldn't be equal because they're so similar, but they are. So this one is going to require a new strategy. Nothing that we've done so far really helps because they're already single terms. Now, if you were stuck and you didn't have this new strategy I'm going to teach you, you could actually start on the left side because you have two terms in the top. And this is going to be another strategy, which may not work here, but you can split up numerators. You can call that 1 over cosine plus sine over cosine. It's the opposite of what we just did in the previous two problems where we got a common denominator. You can't split up denominators, but you can split up numerators. So if I did that, at least it's doing something. And then 1 over cosine is secant and sine over cosine is tangent. But if you look at your target on the left, are we getting closer to the target or further away if we do it that way? We're actually getting farther away because now we have two terms instead of one, and we have it in terms of secant and tangent now instead of cosine and sine. So even though what we did there was not incorrect, it did not take us where we want to go. So here's what we're going to do. You have to pick up on these things from one problem to the next and see why they worked. Remember on this problem here, when we multiplied these two conjugates, secant minus 1, secant plus 1, we got a difference of squared, secant squared minus 1, which gave us a Pythagorean substitution. I can't call 1 minus sine of t cosine of t because it's not squared. But if it were 1 minus sine squared, I could call it cosine squared, yes? Well, how am I going to get it to be 1 minus sine squared? If I had another factor of 1 plus sine right there, yes? And that would make these whatchages? Conjugates. Now, if I do that in the denominator, that's legal so long as I multiply by another one in the numerator. That's just multiplying by a clever form of 1. So multiplying by a conjugate over a conjugate is a huge strategy that comes into play a lot of times. If you ever have 1 plus or minus a trig function, or a trig function plus or minus 1, or even a trig function plus or minus another trig function, if you multiply by the conjugate over conjugate, it'll set up a difference of squares, as you'll see, which will set up a Pythagorean substitution. Let's go ahead and try it out. Let's just keep going in the denominator. 1 plus sine times 1 minus sine is 1 minus sine squared. That would be the next denominator. Yeah, and then in the next line, I haven't even worked in the numerator yet, that's cosine squared. And if you compare that to your right side, now you have at least one of the factors of cosine that you need. You'll have to get rid of the other factor of cosine. Okay, and we'll see what happens when we do that. Now, there's another way to think about it. Instead of setting up a difference of squares, you can also think about it as creating what you need. Create what you need. What do I mean by that? Look on the left side. If you start on the left side, you spy a cosine, and you're like, man, I wish it were a 1 plus sine of t, right? You want the numerator to ultimately have a factor of 1 plus sine of t in it. Well, go then and give yourself what you want. Give yourself a factor of 1 plus sine of t in the numerator, which is legal so long as you do what? Put another one in the denominator. So there's two different things that motivate multiplying by the conjugate over the conjugate. Two different strategies. All right, now in the top, do you want to distribute the cosine, do you think? I wouldn't, right? Because remember, on the right side, you want that 1 plus sine of t to be visible, and he's already visible. The other thing is, if you've already thought kind of ahead, kind of like a chess player thinks a couple of moves ahead, I want to be able to factor out one of those factors of cosine, and you can only factor out factors. So you want to expand the conjugates, but leave the other side factored so you could possibly divide something out. And now what happens with one of those cosine factors? They divide out, and you're left with just 1 plus sine of t in the top and just one of the factors of cosine in the bottom. And does that look like the right-hand side? Yes. Churchill also said if you have enemies, that's good. That means that you stood for something in your life. So I'm going to go ahead and say enemies are good. Enemies are good. Okay? Now, by the same logic, you could just have easily multiplied it on the right side, multiplied it, like that's the word, multiplied it, that's the past tense of multiply. You could have multiplied it by 1 minus sine of t over 1 minus the sine of a t. What that does is it sets up a difference of squares there, or it gives you in the bottom the 1 minus t sine of t factor that you needed in the denominator on the left side. And it'll work out pretty much the exact same way. You're just going to be doing it on the other side of the fraction. And that's how you get the right side to look like the left side. Right? So, to distill from this problem, get in the habit of multiplying by a clever form of 1, that's the conjugate over the conjugate, to set up a difference of squares and ultimately a Pythagorean substitution. If you have 1 plus or minus a trig function, or a trig function plus or minus 1, or even sum or difference of 2 trig functions. And then, just to remind you, expand only to conjugates, but leave the other side of the fraction factored so that you can ultimately divide something out. And then you can add to here another bullet point, which was just another way to look at it. I didn't want to insert that. Okay. Add what you need. Add what you need by a clever form of 1. Multiply by a clever 1. Is that the right need? Right. This is the need like kneading bread. Which it could work here, because what are we actually doing with these expressions? We're kneading them. We're manipulating them. We're massaging them into things that we want them to be. Yeah. Okay. How are y'all feeling? Pretty good? Alexis, I told you it was going to be easier than 6.1. Memorize your identities. Memorize some of the strategies. And then just have a fearless attitude, right? Your finger or your stylus or your pencil, whatever you're using, or your pen. Those are your mathematical machetes. Your mathematical machetes that are helping you what? Take the journey into the strange wilderness where you can slash away boa constrictors or overgrown vegetation to get to a path, right? To make your own path. And then you sign up at the end with something that is seemingly random, but could also be motivational or celebratory at the very least. Okay? We're going to stop right there. Tomorrow, your worksheet's due from 6.1. Your quiz tomorrow will be maybe regurgitate any of the fundamental identities. And if I give you something like this, I'll probably just say simplify tangent of x plus cotangent of x to secant x cosecant or something like that. So it'll be kind of like a proof, but it'll be in the spirit of 6.1 where you're just simplifying. And that way you know exactly what you're starting with and where you want to end up. All right, enjoy the rest of your Monday, the last Monday before Spring Fling Monday. Tomorrow morning is sign up at 8 a.m. at the Career Center, so don't